Hi, and welcome to this part 4 of our lesson 8 video that's all about the drill press. And today we're going to carry on where we left off last time in part 3, and that is, well, we've just completed the reamers, so that means that we're going to start off this part 4 by looking at countersinks. Here I have 3 different countersinks. I have an 82 degree 3/8 of an inch, 82 degree ½ inch, and a 90 degree 5/8 of an inch. Why the different angles and why the different sizes? The most popular reason for using a countersink, well, is to chamfer a hole. And when we chamfer a hole, we produce a small tapered or a small angle on the edge of a hole for 3 reasons. Well, the first is to remove the sharp edge, because sharp edges and burrs, well, are dangerous. The second is to help with inserting and extracting parts in the hole. I mean, if we have to insert something into a hole, it's going to go much better if we have a proper chamfer on that hole. And the third, well, is to protect the hole. If we have a chamfer on a hole and we ding the edge of the hole, we'll actually be dinging the edge of the chamfer. And that means that the hole will probably maintain its integrity. So 3 reasons for producing chamfers. But that's not the only reason for using a chamfering tool or a countersink. The other main reason is for flathead screws. Now, flathead screws are screws that we use when we need the head of the screw to sit just below, flush with the top of a part that we're assembling. They don't have as big or as deep a head, and if I look at this 3/8 in both cases, but a flathead and a socket head cap screw, well, I can see that the socket head requires a lot more depth on its counter bore than the countersink will require for this flathead screw. So when we're assembling thin parts, like aluminum skins on wings or things of that nature, well, flathead screws really work well. However, they also are used because the flathead screw increases the surface of contact between the screw and the part that it's holding down. And because of that increased surface, well, flathead screws are much less prone to loosen by vibration than cap screws are. So we have 2 reasons for using flathead screws. And we know that the angle of the flathead screw has to sit properly in a nice V. I mean, it has an accurate V, and we want it to sit in an accurate V. And that is the second reason for using a countersinking tool. And that's why we have 2 angles as well. I mean, the standard countersink, 90 degrees, would be for metric flathead screws, and the standard 82 degrees countersink, what would be for standard imperial flathead screws. Because surprisingly, flathead screws in the imperial system have 82 degree V's on them, and flathead screws in the metric system have 90 degree V's on them. And when using a countersink, well, that means that it's very important to know, do I have a countersink that's 90 degrees or 82 degrees? When you're chamfering a hole, you really want to use a 90 degree countersink. It just makes life a lot simpler. Now, you can use an 82 to chamfer, there's no reason why not to, it will cut the metal. But a 90 degree point has a 45 degree angle on the V, in other words. And that makes your life quite simple if you're working on countersink diameters. In other words, if on your drawing it says countersink to a ½ inch diameter, well, it's a lot simpler with a 90 degree, because every increment you go down, your hole gets larger by twice that amount because of the 90 degrees. What does that mean? Well, let's say I'm countersinking a hole or chamfering a hole, and I want a chamfer that's let's say 1 millimeter deep. Well, if I go down 1 millimeter, my diameter is going to grow by 2. It's easy to calculate, it's easy to figure out. And that you get with a 90 degree. So we know that the 90 degrees are used for chamfering, it's what we prefer for chamfering, and for countersinking flathead screws in the metric system. And the 82 degrees, well, are really reserved for countersinking for flathead screws in the imperial system. Now, why do we have different diameters? Well, you want to choose the diameter that's close to the major diameter of the chamfer or countersink that you want to produce. Never equal to, though, however, that is important. Now, what does that mean? Well, if I was going to a countersink a hole that I had to produce a countersink that would end up at 3/8 of an inch in diameter, well, I have a choice here, this 3/8 major diameter and this 1/2 inch major diameter. I would choose to produce a 3/8 countersink the 1/2 inch, because the last thing I want here is for the countersink to penetrate the surface. I want that countersunk hole to have an angle cleanly right up to the edge. I don't want it bored down and then come to an angle. And that's the danger with using a countersink that's equal to the major diameter of the countersink we need to produce. Here's an example. Now this is what we want and this is what we don't want. Now if we have a countersink that's slightly larger than the chamfer that we need to produce, well, we're going to end up with nice crisp edges that lead out of the surface cleanly. Whereas if we have a countersink that's too close to the diameter that we need to produce, well, there's a reasonable chance that we're going to end up with a small lip that's more akin to a counterbore than a countersink. We don't want that indentation at the start and then the V. We want the V to come right out to the top of the parts. So you want to choose a countersink that's just slightly larger than the major diameter of the countersink that you have to produce. So we have different sized countersinks and we have different angled countersinks. And we know that the 90 degree is our go-to countersink unless we're going to be countersinking a hole for an imperial flathead screw. But what about speeds and feeds? Well, speed, RPM, I recommend 1/4 of your calculated RPM. So cutting speeds times 4 divided by diameter of the tool, and that whole calculations answer divided by 4. 1/4 of the speed, in other words. And why is that? Well, it's a question of surface of contact between the tool and the part. Now, when the countersink starts out its cutting action, it's cutting on a very small surface and can easily bite into the part. But as we progress in depth, that surface becomes larger and larger, and that is a problem because that will end up bringing us to the point where we're going to get a lot of chatter. To avoid the chatter, well, we reduce the RPM, and that gives us a better control on our feed. We don't have to feed in as rapidly when we're turning at a lower RPM, meaning that we can maintain a good chip load. But what about the feed? Well, the feed is a bit like the feed with the reamers. Now we have 3, 4, 6, 8 flute countersinks, and the number of flutes on the countersink is going to determine the speed at which you have to feed into the part. Now we want a easily 0.02 of an inch chip load for each tooth. So you can calculate that by multiplying the chip load that you want, let's say 0.02 of an inch, by RPM, by the number of teeth on your cutter. But really what we want to do is avoid chatter. So we're going to feed this into the part quickly, even more quickly if we have more teeth, because as soon as this starts to vibrate, as soon as it doesn't bite into the part, well, we're going to get ourselves into trouble. So we want a good, very positive feed on countersinks. And if we want these to cut, well, we don't want to dilly-dally on the feed. And that means that we're going to position, feed in, feed out. We don't want to leave this tool rotating in the bottom of the chamfer that it's just cut, because we will get a vibration and a problem with the finish that we're going to obtain. So here's an example of how to use properly a basic countersink.
And there, our 8 holes on our primary surface are complete. So we can now move on to the chamfering operation. Chamfering tools are form cutting tools, and as we've mentioned before, form cutting tools require slower RPM. That's why we're going to change to our bench type drill press. Since it has a double belt setup for speed adjustment, we can set it at speeds lower than 100 RPM. With the tool leaning in one of the 8.5mm holes, we can set the first depth adjustment nut on the depth stop of the drill press, and then back it off by 1/2 turn. Holding that first nut in position, we can then come down on it with the locking nut for the depth stop and lock it in position. This technique will give us an even depth of chamfer on all the 8.5 holes, but if we apply the same logic to the 11mm holes, they'll end up with the same depth of chamfer as well. In other words, all our holes, regardless of their diameter, will have a 1/2 turn depth of chamfer. And when all the holes, regardless of their diameter, have the same depth of chamfer, well, our part looks pretty good. Complete the 6 chamfers on the 8.5mm holes, but before we move on to our 11mm holes and change our chamfer depth, we're going to flip the part over and do the 6 chamfers on the other primary surface. This will save us a couple of setups, and in reality it'll speed up our work. Remember, when you flip the block over, keep everything really clean. Note here that I'm not leaning the drill press vise up against a pin, and the reason is simple. A chamfering tool never actually is a prisoner of its own hole, so there's no way that you can jam a chamfering tool in a hole, and that's why I'm not worried of snagging the part. So I've completed my 12 chamfers on my 8.5mm holes. I can now move on to the 11mm holes. As you can see, I'm using the same technique, and I'm still going to back off by 1/2 turn. Remember, that'll maintain a certain constants on our chamfer depth, regardless of the diameter of the hole. Once I've completed my 2 chamfers on my 11mm holes on this side of the part, I can flip it over without changing any depth settings and do the 2 holes on the other side. And there you have it, 16 chamfered holes, chamfered at a constant depth regardless of their hole diameter. Exactly the kind of attention to detail you'd expect from a professional craftsperson.
And that brings us to counterbores. And counterbores are used to sink cap screws into the part that they are going to be holding. Now, counterbores are generally used with cap screws for accessibility reasons. Obviously, once this screw is sunken into the surface of the part that it's holding, well, we don't have access to its outside diameter anymore. And that means that we're pretty well restricted to using a socket, not a socket, but a hex wrench or a Torx or something similar that grabs on the inside rather than on the outside of the head. In order to understand the sizes, well, let's use these two as an example. I have a socket head cap screw, a 3/8 here, and the pitch or the number of threads per inch, I should say, does not matter here. and I have a standard 3/8 counterbore. Now 3/8 doesn't mean that it measures 3/8. 3/8 means that it is conceived to produce a counterbore for a 3/8 cap screw. And if we measured both, well, we'd discover that the cutting surfaces of the counterbore are going to produce a hole that is larger than the diameter of the head of the screw. And that is perfectly normal. We want the diameter of the head to be inserted into the counterbore hole. And we'll also discover that the guide on this counterbore is going to be just slightly smaller. It should be somewhere around 3/1000ths of an inch smaller than not the diameter of the screw, but it should be smaller than the diameter of the clearance hole of a 3/8 screw. A standard clearance hole for a 3/8 screw is 1/32 of an inch larger than 3/8, and this guide here should be just smaller than that. So let's measure these and see what we have. If I measure the cutting diameter, I have about 600,000ths of an inch here. And if I measure the head of this 3/8 screw, well, I have about 550,000ths of an inch. So that means that we have somewhere around 50,000ths of an inch clearance between the hole that we're going to produce the counterbore and the diameter of the head, 25,000ths per side, and that's about normal. Now, if we measure the guide here, I have 402,000ths of an inch, and the clearance hole for the standard clearance hole, 1/32 of an inch over 3/8 in this case, well, is going to be 406,000ths of an inch. So that means that we have about 4,000ths of an inch clearance between the clearance hole and the guide on the counterbore here. And that's about 2,000ths of an inch per side, and that is just fine as well. So what about speeds and feeds for these tools? Well, we want again a reduced speed so that we can have better control on our feed. Again, these tools tend to chatter quite a bit. So what are we going to do? Well, with our reamers we reduce the speed, and with our countersinks we reduce the speed, and in this case we're going to do it also, but we're going to reduce it to 1/4 of the calculated RPM. And we're going to reduce it to that much because we want to be able to maintain a good chip load, and we want to be able to reduce the amount of pressure that we apply on our handle. Because on most drill presses that's a problem. The faster you turn, the harder you're going to have to push to maintain a decent chip load. That being said, 1/4 of the calculated speed would be fine for most counterbores. And as far as feed goes, well, like I mentioned, you want to maintain a good chip load. So I would say for a large counterbore or anything about a 3/8 1/2 inch or bigger, well, you want to maintain somewhere around 2,000ths of an inch per tooth. So that means about 4,000ths of an inch per rev, and that's quite a good feed for these tools. Now obviously, the bigger the tool gets, the more feed you're going to want to use, the heavier chip load you're going to want to use. But for most of the jobs around the shop, in the home shop, about 4,000ths per rev will do just fine. So here's a little clip, just like the last clip. This one is taken from our 1, 2, 3 block project video, the part 2 of that project. And we're going to be looking at the counter boring of an M10 by 1.5 hole on a radial arm drill press.
In this case, we're going to be using the positioning tenon on the end of a counter boring tool to position the tool directly above the 11mm holes that we produced earlier. Obviously, since the tool's tenon guides itself in the hole and the tool is going to be in rotation, make sure that it fits freely in the hole before you start this operation. We don't want any leftover chips from a previous operation to skew our positioning, so make certain everything's clean. We're going to be using two parallels to raise the part in the vise. This will position our primary surface above the vise jaws. That'll help us a great deal when we move the tool for our measuring operations. In other words, we won't have to worry about hitting the vise jaws with the tool's tenon. This form cutting tool requires slow speeds, so set your RPM to about 60. Then, using the radial arm and the floating head, position the tool's tenon into one of the 11mm holes. Once in position, make certain that you lock the floating head on the arm and that you lock the arm onto the column. We don't want things moving around here. You can now start cutting, but be careful. Huge amounts of pressure are required to perform this operation. If you don't have a radial arm drill press, well, I'd suggest that you use a good vertical milling machine, but use your Z-axis to feed the part into the tool rather than using the quill. That, in many cases, just wouldn't be able to take this kind of pressure. As I've said, a lot of force is required for this cutting action, so cool the tool down regularly, because force equals heat when cutting. Once the tool is well engaged into the part, you can unlock the radial arm and only the radial arm. This will permit you to swing the tool out of the way and clear the work surface without losing your position in both planes. And now we have some room for measuring. Since we're just starting out in the shop, we're going to use the slowest but safest measuring technique, and that is the cut, measure, and do it often technique. And we're going to continue cutting and measuring until we get to the depth that we want for this counterbore. Bring the radial arm back to its position, lock it in place, and continue on machining. When your first counterbore is complete, we can move on to the second counterbore and redo the same series of operations. So there you go. Our counterbores are complete. We can now pull the part from the vise, and whatever you do, don't go and produce two counterbores on the second primary surface, because only one of the two surfaces incorporate counterbores. All that's left now is deburring the counterbores.
So counterbores are really nice tools to use, but as you could see on that clip, we really need a lot of cutting pressure. So don't use small, delicate machines for this type of operation. And also remember that it is crucial that you have clearance between the guide and the hole that it's inserted into. 2-4 thousandths clearance, somewhere around there, 2 per side is about acceptable. And it is really a good idea to lubrify the guide that is in the hole. Now, a good cutting oil is all you need for that. But what about spot facing? Well, a spot face is a counterbore with mommy issues. A counterbore that would be performed just on the very lip of a hole, just to clean up the surface around that hole, well, that would be spot facing. And spot facings, like counterbores, are used to sit the head of a screw fastener. But it's not made to sink it into the part. It's really just to produce a flat surface upon which the head of a screw can rest. Now, if counter bores were generally used with socket head or cap screws, well, a counter spot facing is generally used for hex head nuts or screws. And that means that they need to be quite a bit larger in diameter relative to the guide size of the tool. And really the only difference between a counterbore and a spot facing tool, well, is that the diameter of the cutting lips is much greater comparatively to the diameter of the hole that you're spot facing. Where would we use spot facing? Well, spot facing is generally used on castings because oftentimes you're going to want to sit the head of a bolt onto a casting but don't need to machine the whole surface. Spot faces will give you that nice clean surface to rest the head of the bolt on. Now, I don't own any spot facing tools, so that's all I'm going to say about that type of operation. And that brings us to taps and tapping on the drill press. And that, well, there's several ways of doing it. The three most basic ways are using the tap inserted directly into the drill chuck and without using the power on the machine, but rather tapping by hand. Well, we can tap a hole or at least align the tap in the hole that way. There's also the method of using a spring-loaded center to guide the tap throughout the whole of the tapping operation. And finally, well, there's tapping heads, and that's something that's really nice to use. I'm not going to get into tapping more than that because we covered that in great detail in our bench work lesson video. It was the part 4 of that video, but here's a few excerpts from that video showing these 3 basic techniques. But these T-handle wrenches are really practical in 2 types of situations. When we have reduced access and a smaller version of a tap wrench is easier to get into certain places, and the other is if our tap doesn't have a center hole on its tang and we need one, because this one doesn't, but some T-wrenches have center holes on the end, and that means that when a tap is in this T-wrench, I can use a spring-loaded center to align the tap in the hole, and that's really practical. So let's go take a look at how this setup can work. So I want to tap a 1/4-20 thread, so I've chosen a 201 thousandths of an inch drill, and I've pre-drilled a hole in this block of mild steel. And we can see that the block is clamped to the table and that the table is locked in place, because for this operation to work I have to maintain the alignment of the drill and the hole until my thread is well underway. And we can see here that we're still lined up, and we can see that I've given myself a lot of room here, because what I'm going to do now is I'm going to remove this drill, I'm going to replace the drill with this spring-loaded center, and I'm going to use this to guide my 1/4-20 tap into the hole straight with my center hole in the T-handle. So let's set this up. Now we can see that this is quite practical because I can turn forward and back up, and since I'm spring-loaded here, well, I can go both ways and I can tap through. But we can also see that this is quite awkward. This is a very small handle and it's not easy to work with. So since I'm well engaged into the part, now would be a good time to retract and remove this setup and bring my part and my tap over to the bench vise and finish this job with a proper tap handle. So let's say you don't own a T-handle with a center hole in it, and you don't have one of those spring-loaded centers to guide your tool. Well, you can still use your drill press to guide your tool straight into your hole. And for that, well, we have our part with our pre-drilled hole, 201 thou for quarter 20. I have my starter tap, or my taper tap, that I'm going to install into my drill chuck and snug down, but I don't want to kill it. Just good and snug, but not murderously tight, okay? Because if it's going to slip, I'd rather it slip here than break. Now, this is not a good situation. We shouldn't use power when we're doing this, at least not at the start. And if you do, well, you do it at your own risk. But we can still use the alignment without using the power, and here's how. And first off, we want to make sure we don't start the machine, so let's unplug it. I mean, these little removable switches are nice, but unplugged is definitely not going to start. So my machine is unplugged. I'm going to, and I've left a lot of room here, and you'll see why in a few minutes. I'm going to bring my tool down to my hole and engage it. Note that I'm maintaining a light pressure here, but as I turn the tool into the part, this continues on its downward movement. Now, my tool is engaged by 2.5, 3 turns, and that's about what I want here for it to be stable and straight and well engaged. I do not let up on the pressure here. Light pressure continues to bear down. If I let go of this, the spring-loaded handle is going to draw my vise up and probably break my tap. So I maintain a light pressure, and I keep my key close at hand, and I loosen the chuck, and now I can come right up. And that's why I left myself a lot of room here. Now I can work, and I can complete the tapping operation with a proper handle. But this isn't the right place to do it. This is a floating vise and it isn't stable. So what am I going to do? I'm going to remove my part from my vise. I'm well engaged, good and straight. Head over to my bench vise, my stable third hand, and there I'll complete this using the proper tap handle. Now, what we have here is a tapping head, and it's definitely not something that you're going to want in your home shop. It really is a production tool for tapping many holes in a part, or many holes in many parts. It really accelerates production. Now, why am I showing it? Well, it's good to be exposed to different things. Now, remember, if you expose yourself in public, well, you're going to get arrested, and that's not a good thing to do. But it's good to get exposed to new things. So even if this isn't a home shop tool or for beginners, well, it's still nice to know that it exists. So let's start at the bottom here. I have my part that isn't fixed to the table, it's floating, and that way I'll be able to move from one hole to the next quickly. And I put it in a vise so that I have some mass that will counteract the force of the tapping. So I have pre-drilled 5 holes, and they are not through holes. Since they don't go through the part, I'm going to be using, for a production tap, my spiral flute tap that's going to pull the taps, the chips upwards and clear them out of that hole. Next, we take a look at my tap itself. It's a helical flute tap, and it's mounted in the tap holder of the tapping head. That is a floating tapping holder. If I can see, there is some movement sideways, up and down. It's not perfectly fixed in there, and it is spring loaded. Now, this tapping head does 3 things. It gives me that floating action that permits me to tap with power, so the machine will align and rotate this tool into the part. Because it's floating, it gives me a little leeway here. But it also has a reversing action to it. So this will feed down into the part And once I change direction, once I pull up on the spindle, this tap will change directions of rotation and will spin out of the hole. So it can spin down, it floats, it has a reverse. And it also, and this is important, has a viscous clutch. Now this clutch will apply a certain amount of force on the tap. And if I exceed that force, well, it's just going to spin, okay, or slide. And that's going to save me from breaking my taps. And I've already set this clutch at a level 2 for my 1/4 inch 20 tap that I'm going to be using. And finally, well not finally, but almost finally, we have this arm. If I want the planetary gears and the reversing action to work, I have to block the rotation of at least part of the gear train. And that's what this arm does against this stop. But it still has to be free to move. And that's why it just leans up here and it can still float up and down freely. And finally though, we're going to be using tapping oil to help with the tapping action and the cutting action here. So let's take a look at what this looks like when it's actually cutting. Well, that was fun to see. And like I said, it's not a tool that we're going to use or that we would use in a home shop, or it's not a beginner's type tool. But it's nice to know that it does exist and to see how it works. Well, that's about everything for this time. But before I leave you, I'd like to draw your attention down here and just say that I'm ribbing here my Australian friends, but more particularly someone who's called Emma Ritson, who has a site that is called Emma's Spare Room Machine Shop. She does great stuff and I find it quite interesting and entertaining. So if you have a few minutes, go check out her channel. Now, until we meet again in part 5 of this lesson 8, all about the drill press, well, have fun, be safe, and happy machining.
There you go.